In this video, we're going to solve some homogeneous linear differential equations with constant coefficients. This is assignment number 5, question number 4, question set 4. There are a number of questions that we're going to look at. Let's take a look at the first question. So the first differential equation that we're going to solve is y double prime plus y prime minus 6y equals 0. So what are we going to do? We have constant coefficients and it's homogeneous. So we can use our assumed form. So we first assume that y is equal to e to the mx. Okay, so that means that what that means is that y prime is equal to m e to the mx, and y double prime is equal to m squared e to the mx. If we sub this solution for y into the differential equation, we get m squared e to the mx, right, plus m e to the mx, okay, plus e to the mx equals 0. Okay, so what we can do is we can factor out e to the mx, and then we get m squared plus m plus 1 equals 0. Now, e to the mx will never be 0. Okay, so we could divide it out from both sides if we like, right? If you want to see it like that, and this is gone, and that's still 0, right? So basically what we need to do is we need to find where m squared plus m plus 1 equals 0. We need to find the roots of this equation. Okay, so look, what we need to do is we need to find, in order to factor this, what adds to 1, okay, and I forgot something here. There's one issue here. You see 6? Okay, 6, it should be minus. So let's erase here. This should be a minus 6 e to the mx. So this should be plus 1, but it should be minus 6. Okay, so what do we have? What adds to 1 and multiplies to negative 6? Well, that's m adds to 1, plus 3 and 2, 3 and negative 2. Okay, so they are going to add to 1 and multiply to negative 6, and that equals 0. Okay, so we've factored the polynomial. Okay, you could use the general quadratic equation if you like, but here it was a simple factor here. So what are we going to do next? Well, next, basically what we found that the eigenvalues are negative 3 and 2. Okay, these are our eigenvalues. Values. Okay. So we need to sub these eigenvalues back into the assumed form of the solution. So we have two particular solutions. y1 is e to the negative 3x, and y2 is e to the 2x. Okay, so these are the particular solutions. Now, these are the eigenfunctions. Okay, now because they're linearly independent and they're linearly independent solutions, okay, what that means, and here we have two solutions because we have a second order differential equation. Okay, so the solution space, because these eigenfunctions are linearly independent, okay, what that means is that we can they can form the basis of the complete solution space. Okay, and the way that they form a basis for the complete solution space is via linear combinations, or the scaled sum of the two eigenfunctions. So we have C1 e to the negative 3x plus C2 e to the 2x as the general solution. Okay, so this is our general solution. And again, we're basically, if you were to sub this general solution into the differential equation, okay, the left-hand side would equal the right-hand side. Okay, and that, if you wanted to check, that's what you would do. You check the left-hand side and show that it equals the right-hand side, and therefore it must be a solution. Okay, let's take a look. So these are two real roots to the characteristic equation that are different from each other. That's one possibility when you have a quadratic equation and you solve for its roots. Okay, let's take a look at another example. I'm going to erase this one, or I can go right here, say clear canvas. Beautiful. Okay, let's see another example. So in this example, we have 2 y double prime minus 16y prime plus 32y equals 0. Again, it's a homogeneous linear differential equation. Now, we could simplify this even further by dividing the entire equation by 2. Okay, so we'd have y double prime, we'd have minus 8y prime plus 16y equals 0. That just make our life a little bit simpler. Okay, again, to solve the differential equation, we assume the form of the solution, and that is, we assume that y equals e to the mx. You can say y prime is m squared, right? Or sorry, y prime is m e to the mx. Sorry about that. E to the mx, and y double prime is equal to m squared e to the mx. Okay. So we're going to sub this into our differential equation and then factor out the e to the mx. So we can go straight to the characteristic equation, as that's all. Anywhere you see y double prime, that's basically m squared, right? Minus 8m plus 16. Okay, so that's what we have here, and this equals 0. We would have factored out the e to the mx and divided anyway. So we have the characteristic equation. Now this characteristic equation has two roots, right, where it equals 0. And so what we need to find is we need to find something that adds to 8 and multiplies to 16. And so negative 4 and negative 4, right? So if you had m minus 4 times m minus 4 equals 0, okay? What you have is you have repeated roots, right? So you have that m equals 4, but it equals 4 twice, right? So we have y1 is equal to, y1 is e to the 4x, okay? And basically what we found is whenever you have a multiplicity, right, the complete solution, and basically what we're saying is that the other solution, if you look at the formula, is that the next solution is x times e to the 4x, right? And if there were 3 solutions, right, then the other solution would be, if this was third order and you had 3 repeats, it would be x squared e to the 4m. Okay, so basically the general solution, y is what we said. We said e to the 4x. The formula that we saw was c1, right, plus x times c2, right? It would be c1 e to the 4x plus x c2 e to the 4x, right? And so that's what we found by doing this, right? The general solution, if you have multiplicity, is y is equal to e to the mx, and then we'd have c1 plus x c2 plus dot 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 plus x to the m x to the n minus 1 c m, basically. Okay, so we saw this. This is how we deal with the repeated roots. So here's our general solution. Okay, so that's repeated roots. So for the first problem we saw was two real but different roots. Here are two real but repeated roots. Okay, so that's how we deal with that problem. Let's take a look at another problem. Let's go clear canvas. Okay, let's look at another problem. Here we have, we'll start off with 2y double prime plus 16y prime plus 82y equals 0. Okay, I can simplify this a little bit further. Divide both sides by 2, you get y double prime plus 8y prime, 41y equals 0. Okay, again, like before, we assume the form of the solution. Let's assume here, sorry, my palm touched the, is y is equal to e to the mx. Okay, so that means, again, y prime is m e to the mx, y double prime is m squared e to the mx. Okay, so now if we sub this into the differential equation and then factor out e to the mx, we get our characteristic polynomial. And so what I'm just going to do is wherever I see y double prime, I'm just going to put m squared, right? Plus 8. Wherever I see y prime, I'm going to put m. And wherever I see y, I don't put anything. I just put 41. Right? We would have had the e to the mx and equal to 0 when we subbed into the differential equation. Okay, so now what we need to do is we need to find the roots of this, because that's the only way that the left-hand side is going to equal the right-hand side. So we need to find the values of m. We need to find the eigenvalues by, again, factoring this. Now, this is not easy to factor, so what I'm going to use is I'm going to use the general quadratic equation. So the GQE is that m, in this case, or x, is equal to negative b plus or minus square root b squared minus 4ac over 2a. So a general quadratic formula. So what do I have? I have that m is equal to, okay, negative 8 plus or minus 8 squared is 64 minus 4, a is 1, and c is 41. Okay, all divided by 2. And what do I get? Well, what I get is I get negative 4 plus or minus 64 minus 164 is negative 100, right? So this is negative 100. So the square root of that, right? So I would have, I already divided the negative 8 by 2. So what I have is it's the square root of negative 100, which is 10i divided by 2. So what do I get? I get negative 4 plus or minus 5i. So what do I have? I have two complex roots. I have that m equals, let's see here, is negative 4 plus 5i, and m equals negative 4 minus 5i. These are my eigenvalues. Okay, so I need the eigenvectors are going to be, you basically I'll just write the general solution. Here, let me move my screen up a little bit and zoom out. Okay, so I'm going to write the general solution is that y equals, okay, it equals e to the negative 4 plus 5i c1 plus c2 e to the negative 4 plus, actually minus 5i, negative 4 minus 5i. Okay, so that's our general solution. Okay, now what we can do, and I showed this before, we can use the formula or we can just do it from first principles here, is that what we essentially have, okay, is that we can use Euler's formula. E to the I theta is cos theta plus I sine theta, correct? So if we sub that in, if we take, what effectively we have here is we have C1, okay, and I forgot the x here, sorry about that. So here, the final solution here, multiplied by x, and this one is multiplied by x as well, okay? So it becomes C1 e to the negative 4x, okay, times e to the 5i, that's the first one, times x, okay, plus c2 e to the negative 4x, right, times e to the negative 5i x. Okay, so what we can do is we can factor out this negative 4x. So we have e to the negative 4x. That's the real part. Okay, you notice that's the real part. And again, you're going to see the formula that we saw in class. E to the negative 4x. So you have c1 e to the 5ix plus c2 e to the negative 5ix. Okay, and if you sub in you can sub in the Euler's formula here, and you'll get the cos and the sine. Okay, if you do that, okay, if we do that, let me move this up here. If we do that, what we get is we get e to the negative 4x, and then you get your c1 and your c2. You get c1, okay, and here I'm going to go cos 5x plus I sine 5x, okay, all right, plus c2, and now look, cos of negative 5x is equal to cos of positive 5x, right? So we have cos of 5x. Now, sine of negative 5x equals negative sine of 5x. So equals I minus sine 5x. Okay? And we can combine these if we like. All right, so what we can do is take the coses, bring them together, and those are the real parts, and then the imaginary parts we can also bring together. So what we have here, we have e to the negative 4x, okay? We have, if we take c1 plus c2, right, we can combine them, right? That's how many cos of 5x we have. And then we have the c1, right, and minus c2, right? So plus, and here we have c1 minus c2, again times I, and then times sine of 5x. Okay. So the way we did this before, we called this one constant, and we called this another constant. I'm just going to put a fancy C1, and I'm going to put a fancy looking C2. It's different than the other ones. Okay, so that means that our solution, okay, is equal to e to the negative 4x, right? And then we have C1 cos 5x, right, plus c2 sine 5x. However, c1, this fancy c1, is or little c1 plus little c2, and the fancy c2 is complex. Okay, so this is little c1 minus little c2 times I, and this is, sorry, the fancy c2. Okay, so this guy is complex, basically, is what we're saying. Okay, so that's our general solution. And again, there is a formula, but this is just a little easier. You don't have to remember formulas. Okay, so that's if you have complex roots. Okay, let's take a look at another solution. Okay, another problem actually. Okay, let's go here and clear the canvas. All right, let's take a look at one last problem. So our differential equation here is y double prime plus 2y prime minus 2y is equal to 0. Okay. Now we can go straight to the characteristic equation, right? So we can say, okay, m is going to be m squared plus 2m minus 2, right? If we again, we made the assumption that y equals e to the mx, right? Okay, so basically this must equal 0. It would have factored out the e to the mx here. We can cancel. So this is 0 when? Well, this is hard. Now, what adds to 2 and multiplies to negative 2? Not really anything that we can easily see. So we're going to use the general quadratic formula again. So here we go. It's the general quadratic formula is m equals minus b, so minus 2, plus or minus square root of b squared, so that's 2 squared, minus 4 times a, which is 1, times c is negative 2, over 2a, which is 1. So our solution is m, or the eigenvectors are negative 2 plus or minus 4. Okay, so this is 4 plus 8, right? Which is root 12, all divided by 2. So the real part is negative 1 plus or minus. Now root 12 is what? Okay, we're going to move over to. It's root 4 by root 3. And really, root 4 is just 2. So we can cancel that out. And we get minus 1 plus or minus root 3. Okay, so that's m. So these are our eigenvalues. So m equals negative 1 plus root 3, and m equals negative 1 minus root 3. Okay, so if we combine, we know our particular solution, so let's get the general solution. So that's y is c1 times e to the negative 1 plus root 3 plus c2 negative 1 minus root 3. Again, I forgot the x. Okay. And that's it. That is our general solution. Okay. I hope you enjoyed this video, and see you next time in math class.